In chapter 3, we're going to be looking at sequences and series, something you should be familiar with from Calculus 2, or even more if you've taken an introductory analysis course or analysis on the real line. The basic facts about convergence uh, that we learned maybe in an introductory to analysis class, or we're just going to expand them to a more general setting. So these first three sections, I believe, are actually the first two, if I'm not mistaken. We're going to be concerned with sequences in Euclidean spaces or sometimes in metric spaces. So we'll begin with our first definition, what a convergence means. So a sequence, P sub n, in a metric space X is said to converge if there is a point P in X with the following property. So for every epsilon greater than 0, there's an integer n, big N, such that little n big greater than or equal to big N implies that the distance between the point Pn and P is less than epsilon. Now, if Pn doesn't converge, then it is said to diverge. So a picture for that, let's say we have this, before I even go on to range, a sequence. So for example, let's call this the sequence P sub n. Right, I'm going to have a point here, then a point here, a point here, a point here. And let's call this point P. So here, this is P sub 1, P sub 2, P sub 3, so on and so forth. Right? So it converges if after a certain n, so for example, let's say this n here, n is the 40th point in the sequence. So it's P sub 40, that point. After that point, all the points are arbitrarily close to point P. So they're an epsilon distance from from the point P. This isn't the best drawing for that. In fact, let me erase it because I think it would do you a disservice. But given an epsilon, say epsilon is, let's say, 1/2, right? So point P. Let's do it like this. Point P, this is a radius of 1/2. I know it doesn't look like it's centered at P. Let's just assume it is. So this is 1/2, right? Now the points in the sequence P sub n, let's say, are these points. But after a certain point, they get close. They get arbitrarily close to P sub n, and now they're within the epsilon ball of P. So if there's always an n, no matter how small we make epsilon, if there's always an big N, such that if little n is greater than or equal to Pn, big N, then Pn, the distance between Pn and P is less than epsilon. That's what the convergence means. Just like convergence on the real line, but now we're just looking in general metric spaces. I know this looks like R2 because where it's like a plane, it's a ball, it's a circle. But that's the definition in just in general, in general metric spaces with our distance function. Okay, so now we can take a look at what we mean by the range of P. So the range of P is just the points that get mapped, right? Because a sequence maps numbers, the natural numbers, to, you may have recalled that it maps them to real numbers. It can also be complex numbers or other sets, which I'm just going to call A. Well, a sequence Pn is bounded if the range is bounded, right? So again, the range is just all the points that get mapped. All the points of the sequence, those are the range. So here we have different sequences of complex numbers. We're gonna see if they're convergent, what their ranges, and if they're bounded. So first one, 1 over n, does that converge? It does. It converges to 0. So this one does converge. Converges, that's an arrow, to 0. What's the range? Well, all the numbers 1 over 1, 1/2, 1/3, so on and so forth. That's the range. Is it bounded? Well, it is, right? Because the biggest number it's going to have is 1, which is 1 over 1. The smallest it can have isn't 0. It'll never be 0. But it will be, all the points will be greater than 0, right? So it's bounded between 0 and 1. So this one is also yes, right? In this case, the range, instead of just saying what the range is going to be, I'm just going to put, is it infinite, finite? So here I'm just going to put, this is an infinite range. Right, there are infinitely many numbers in the form of 1 over n, where n is a natural number. Okay, so our next one, Sn is equal to n squared. Is that convergent? That actually does not converge. Right, n squared just keeps increasing forever. What about its range? It is also infinite. Is it bounded though? This one is not bounded. And a good exercise would try to pause the video and try to fill in the rest. I'm just going to go ahead and fill them out now. So this next one, we know this converges to, let's see, what converges to 1. So it does converge. It converges to 1. Range is, it is infinite. Wow, that's way out of the box. It is infinite. And is it bounded? Yes, this is bounded. Okay, next one. I to the n, where I is the square root of -1. Does this sequence converge? No. And I think they show you this problem in high school, some high school class. Does it have infinite or finite range? Or it just has a finite range, right? It's only 4 different numbers. So if you remember, I to the first power is square root of -1, I squared is -1, I to the third is -1 times square root of -1. I to the fourth is 1. And then I to the fifth goes back to square root of -1. So it's only 4 different points, 4 different points in the range. Therefore, it's finite. Is it bounded? Absolutely. What about this last one? If it's always 1, well, it converges to 1. So it does converge, yes. Is it range is infinite or finite? Well, it's just 1, right? So it's finite. And is it bounded? Absolutely. I was gonna write absolutely. I'll just put yes. It is bounded. So now we're gonna summarize some important properties of convergent sequences in metric spaces. So these are some important property. If P of n, let P of n be a sequence in a metric space X. Well, P of n converges to P in X if and only if every neighborhood of P contains P of n for all but finitely many n. right? So all the points of the sequence are in every neighborhood except for finitely many. Second one, if P is an X and P prime is an X, and if Pn converges to both P and P prime, then P is equal to P prime, meaning a sequence can only have one limit. It can't have two different limits. If P sub n converges, then P sub n is bounded. Next, if E is a subset of X, and if P is a limit point of E, then there's a sequence P sub n in E such that P is equal to the limit of Pn as n goes to infinity. These are fairly straightforward proofs. We'll go over them. So first one, proof of A. A is probably the longer one because it is biconditional. So first, suppose P sub n converges to P and let V be a neighborhood of P. Well, for some epsilon greater than 0, the condition Q, the condition of the distance between Q and P less than epsilon, where Q is in X, implies that Q is in V. Right, because it's in that neighborhood. So it must imply that Q is in V. Well, corresponding to this epsilon, there exists an n such that little n greater than or equal to big N implies that the distance between Pn and P is less than epsilon. Right, so for any epsilon, the points after, let me draw this actually. Let's say this is P. Let's say this is the epsilon neighborhood. Epsilon ball, I'll write ball with radius epsilon centered at P. That's what that notation means. After a certain n, so n plus 1, all the points lie in this neighborhood. So what does that mean? That means that from n all the way to 1, all of those points were outside the neighborhood. And how many are there here? Well, finitely many, right? So that's where we're going. So therefore, n is greater than or equal to n, which implies that Pn is in this neighborhood of V. Right? What I was saying, that all these points from Pn. So that's how we get that direction. The next direction, we're saying, suppose every neighborhood of P contains all but finitely many P sub n. We're going to fix epsilon greater than 0 and let V be the set of all Q in X such that the distance between P and Q is less than epsilon. So basically, V is a set of points that are within epsilon distance of P. So by assumption, there exists an n corresponding to this V such that P sub n is in V after n is greater than or equal to n. Therefore, all those points P sub n, the distance between all those points P sub n and P are within epsilon, which we had said. Therefore, P sub n converges to P. If you need, go ahead and pause. Make sure you understand every step. Now we move on to 2, showing that a sequence only converges to one limit, not two, or multiple, only one. So let epsilon greater than 0 be given. There exists integers big N and big N prime, such that n greater than or equal to big N implies that P sub n, the distance between P sub n and P is less than epsilon over 2. And the distance between P sub n and P prime is less than or equal to epsilon over 2. So here we're just, notice up here, we're saying, oh, sorry. if P sub n converges to P and P prime. Well, what does that mean? By definition, it means this here and this here, right? And actually, in fact, this should have a prime. A prime right here. There we go. And again, let me draw a little picture to help us understand this before we move on. So let's say this is P, this is P sub n. Can a sequence converge to both of those? Well, actually, before I even say that, I'll just draw the picture. Let's say this is a neighborhood. This is a neighborhood of P prime. Well, a sequence is only gonna have all of the terms of the sequence in this neighborhood, except for finitely many, meaning there can only be finitely many inside this neighborhood, which is kind of gonna lead us to nonsense. But here, this is just a direct proof. So we're gonna choose n greater than or equal to the max of both n and n prime. Why? So that we have that this condition is met for both of these. Well, we have that the distance between P and P prime is less than or equal to the distance between P and P sub n plus distance between P sub n and P prime, triangle inequality, which is less than epsilon, right? Because this here was epsilon over 2 and epsilon over 2. That's why it's less than epsilon. So the distance between P and P prime is arbitrarily small, meaning, oh, I guess that concludes the proof. I didn't write the conclusion. Meaning that P and P prime are indeed the same point. So if this illustration over here, like I said, helps you, remember we can only have all but finitely many points of the sequence in this neighborhood. So there can only be finitely many in here in this neighborhood, which kind of leads us to a contradiction because, well, a finite set can't have a limit point. So that was a direct proof of that. Proof of C, if P of n converges, then it is bounded. Fairly straightforward. There's an integer n such that n greater than n implies that the distance between P sub n and P is less than 1. So here, we're basically setting epsilon equal to 1. So again, little picture. Let's say this is P. We have a radius of 1, which is equal to epsilon. An epsilon radius. We're going to put R as the maximum between 1 and every point between 1 and the distance between P and every other point that's not in the neighborhood. So let me draw a picture for this to make this easier, a better picture. Let's say this is our limit point P. And let's say this is our neighborhood, a ball with epsilon radius. So actually epsilon we're choosing just to be 1, so 1 centered at P. So what points are in here? All the points that after n, P sub n plus 1 is in here, and everything after that, n plus 2 and plus dot dot dot, right? It's just a bunch of points, infinitely many in fact. But all the rest, the n minus, n, p sub n, p sub n minus 1, p sub n minus 2 are not necessarily in the neighborhood. They may be outside. Again, they may very well be inside, but they can also be outside. So we're just going with the outside case. Now the reason we put r to equal the max between 1 is because if all of them are inside all the points, well then the max will be 1, right? Because if all the points are inside, well then the distance between p here and all the other points is less than 1, so our max would be 1. But if they're outside, in this case, p all the way to pn minus 2, assume that's a straight line, that distance is greater than 1, and it's actually the greatest distance. So we're going to set r to that radius, and guess what we can do now? If that's our new radius, then we can draw a ball and capture all the points of the sequence in that ball. That's why we set the r equal to the radius equal to the maximum of all the distances. Then for the distance between p sub n and p less than or equal to r, for n equals 1 to just infinity, we have that it's bounded and it's done. Okay, another one. Finally, our last one, D. This one may be the shortest. Actually, C is pretty short, so maybe not. For each positive integer n, there's a point p sub n in E, such that the distance between p sub n and p is less than or equal to 1 over n. So we're setting epsilon to be the sequence 1 over n. Right, that's going to be our epsilon sequence, I suppose. Well, given epsilon greater than or equal to 0, we choose n such that n is greater than or equal to epsilon. Why is that? Well, so that epsilon can be greater than 1 over n. Do some bit of algebra there. So that if n is greater than or equal to big N, the distance between p sub n and p is less than epsilon. Therefore, p sub n is equal to p. Okay, so we're going to move on to some algebraic properties or algebraic operations, I should say, of sequences. Multiple theorems. It's going to be a pretty long proof, but because we have multiple theorems, nothing too complicated. Suppose Sn and Tn are complex sequences, and that their limit is S and T respectively. Well, then the limit, if we add the sequences together, their limit, the limit of that sequence, sorry, is just S plus T. Again, you may have seen this already in Intro to Analysis course, but now we're just dealing in just a metric space or with complex sequences. The limit times a constant, the limit of a sequence times a constant is just the limit of the sequence times the constant. Similarly, if a sequence you just add a constant, the limit is just the limit of the sequence plus a constant for any constant. And that proof is actually pretty straightforward. You can use A to kind of like show you an outline, to help you make an outline. But the proof for B is fairly straightforward. C gets a bit more complicated. The limit of two sequences being multiplied is indeed their limits being multiplied, the product of the limit. And this one might be the most complicated one. The limit of a sequence that's 1 over S sub n is equal to 1 over S, meaning 1 over the limit of the sequence. And this is only in the case that S sub n is not 0 for all n. and neither is its limit point. So we'll go through the proofs. First one, given epsilon greater than 0, there exists n1 and n2 such that Sn minus S is less than epsilon over 2. So we're just using the definition of convergence of a sequence. Same thing for T sub n, convergence of a sequence. Now we choose n to be the max of those two so that we can get that both converge. And therefore we have that the sequence minus what we're claiming to be its limit is less than Sn minus S plus Tn minus T, which we know both of them are less than epsilon over 2, which is equal to epsilon. Therefore, that's less than epsilon. So therefore, this sequence here does converge to S plus T. Okay, second one. Actually, I want to skip the B. Kind of just follow what was happening here. With the constant, it should be easier than even including another sequence. So I'll leave the B to you. If you do need help, go ahead and I'm sure this is, you can look this up in a book, maybe in Rudin's book. I'm not sure if it's there. Should be, or any other book. But I'm going to omit it to get exercise to try. Now these other hard ones, I shouldn't say hard, but more involved proofs, C and D, we can go over. So we use the identity for this proof that S sub n minus T sub n minus St is equal to this whole expression over here. If you want to do some algebra and verify that, you should. So given epsilon greater than 0, again, there are integers n1 and n2 such that Sn minus S get arbitrarily close. Same thing with Tn minus T. The sequence gets arbitrarily close to its limit point, in fact less than square root of epsilon. So if we take the max and set it equal to n, well, using our identity, we just get this. Which, again, you should probably verify. Therefore, the limit as n goes to infinity of Sn minus S times Tn minus T is equal to 0. What does that mean? That means that we can use this property over here and this property here, also this one, to conclude that in fact this holds true. That's less than epsilon, or as another way of saying it, the limit as n goes to infinity is equal to 0. Therefore, this sequence converges to S, the product of S and T. Finally, D, the limit of 1 over S sub n is equal to 1 over S. This one does require, it's not difficult, but it does require some algebra. So choosing M such that Sn minus S is less than 1 half times S. If n is greater than or equal to m, we get what? We get that Sn is greater than 1 half times S, where n is greater than or equal to m. So given epsilon greater than 0, there's an integer n greater than m, such that n greater than or equal to big N implies that this difference is smaller than S squared times epsilon. Right? This here gets arbitrarily small. And how small? Less than 1 half of S squared. No, that doesn't look right. Let me see. Let me do the algebra. Give me 1 second. Okay. No, yes. This is almost right. This should be less than 1 half of S squared times epsilon. And again, try to do some algebra to verify this. I don't want to go over elementary algebra to use up your time. But now, for n greater than big N, we get this difference. And this, again, just algebra from this step to that step. But we know that that now is less than 2 over s squared times this difference. And we know that is less than epsilon. Again, by doing some algebra from over here. So this is one of those proofs where mathematicians knew what they wanted, like what they wanted to show. In this case, this theorem. So they kind of worked backwards to see how they should set things up. This doesn't just come, the steps don't go, don't just appear in their heads magically. But we're just going to look at one more thing. We're going to suppose, wow, I am missing a bunch of stuff in here. We are going to suppose x sub n, this x sub n in our k and x sub n, we're gonna suppose x sub n is an RK and it's of this form. So here I have it, x sub n. Actually, I should have used black. X sub n is of that form. Then x sub n converges to x equals alpha sub 1. Alpha sub 1 dot 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 all the way to alpha sub k if and only if the limit of a sub jn as n goes to infinity is equal to a sub j. So this is just basically saying, so an R1 sequence of points converges to another point. This is the same thing we're doing. A sub 1 n converges to a sub 1, or in this case alpha, I should say. So all these points all the way to alpha sub k sub n converge to their respective points. That's all that's saying. So we're just dealing in higher dimension Euclidean spaces. But it's the same concept. But we have that these three properties are also true. So suppose xn and yn are sequences in Rk, in a finite dimensional Euclidean space, and beta sub n is a sequence of real numbers, and they all converge to the respective limit. So x sub n converges to x, y sub n to y, and beta sub n to beta. Well, then the following are true. And these properties are really similar to the ones we just saw last slide. Yeah. So we're going to prove we're going to prove A. And that doesn't even show there isn't even an A, right? Oh, yes, there it is. It's right here. Yes, I'm going to prove this here. And I'm going to leave these to you. And why? Well, because just use the theorems from the last slide. It's almost identical. So the proof of A. If xn converges to x, well then the inequalities this here, which just follows from the definition of a norm. If you don't remember the norm, we went over that definition in the first chapter. Show that indeed this does just converges to a sub j. So that's one direction. It's really simple. You just need to know the definition of a norm. But now we can show the other direction. If the limit as n goes to infinity of a alpha sub j sub n is equal to alpha sub j, well, then there's an epsilon greater than 0. No, sorry. For each epsilon greater than 0, there corresponds an integer big N such that little n greater than or equal to big N implies that that difference is less than epsilon over the square root of k. Again, where the heck did the mathematician who proves this get this? He or she probably worked backwards. In fact, I'm almost 100% sure they worked backwards. These just don't come from divine inspiration, but it's going to make this work, and we'll see why. Because if we have x sub n minus x, what does that mean? Well, if n is greater than big N, it means that, by definition again of norm, that this whole sum, the square root of this whole sum squared, is less than epsilon. And again, this has to do a lot with the norm. Make sure you know that. So x sub n does indeed converge to x. And to prove B, look at part A from last slide, and it should be pretty straightforward, the proof. A good exercise to work on. So it's just kind of just introducing sequences, their properties, in Euclidean spaces, sometimes in metric spaces. What it means to sequence, what it means for a sequence to converge, what it means for a sequence to have infinite or finite range, what it means for a sequence to be bounded, so that we can look at subsequences next and Cauchy sequences. Hopefully you're already familiar with those subjects, with those topics. Otherwise, it may be a bit confusing or just hard to digest.